This is a video presentation about wireless power transmission by Brittany,
Elliot, and Sean.
Wireless power transmission is the transmission of electrical energy from a power source without any interconnecting wires. But first, a brief history lesson. In the 1890s, Nikola Tesla dreamt of a world where houses and all of their electronics would be powered wirelessly. His idea was that he could build an 187-foot-tall Wardenclyffe tower that used the earth as an electrical conductor. He also discovered AC, or alternating current, which will relate to our circuit. In the design of our circuit, the coils we used are also based off a Tesla coil. Here we are trying to recreate an example of what Tesla envisioned. We hypothesize that the LED will light up due to the induced current from the alternating magnetic field.
The general idea is that current is running through the first coil connected to the transistor and the battery, acting as the transmitting loop. The transistor turns the direct current into a high-frequency alternating current. That current running through the copper loop creates a magnetic field. This magnetic field is what induces a current and voltage into the second copper loop, the receiving end. As a result, the LED lights up.
The physics concepts that apply to this system include Faraday's law of induction, or magnetic flux, and Lenz's law. Faraday's law of induction states that an electromotive force, or EMF, will be induced from a change in magnetic flux. Magnetic flux is represented in the second equation by B dot A, where B is magnetic field and A is area enclosed normal to the magnetic field. EMF is represented in the first equation by number of loops multiplied by change in flux over time. Lenz's law just explains that the induced current from the EMF will be in the opposite direction of the change in magnetic flux. This is represented in the EMF equation by a negative sign in the equation. So in our system, first the transistor will amplify the direct current from the battery at a higher frequency alternating current. There are three parts to every transistor. The emitter is always connected to the power source. The base pulls electrons from the emitter and sends them into the collector. This produces an alternating current by changing the direction of the current in the transmitting coil. This means that the current is oscillating, so the magnetic field is being produced. Yet, because there is no receiver loop in this circuit currently, there is no area in the magnetic field, so therefore, there is no magnetic flux. However, when a receiver loop is introduced in the circuit, oscillating magnetic field of the transmitter loop produces a changing magnetic flux in the receiver loop with a constant area. This in turn creates an alternating voltage in the receiver loop that is used to light the LED.
Another thing to point out is that an object can be in between the coils and the magnetic field can still find its way around the object to induce EMF.
The materials needed are 25-gauge enamel copper wire, a 27K resistor, a 2N2222A transistor, an LED light, tape, hot glue, and a 9-volt battery. First, we wrapped copper wire around a cylindrical-shaped object 30 times, leaving two ends free. Then we wrapped copper wire around 15 times, pulled out a loop, and then 15 more times. Next, we soldered the wire ends as seen in the figure. Since it did not work with battery on our first try, we tried hooking up the two free ends of the transmitting coil and taking out the transistor, as seen in the last photo, but this did not work either. One problem we had was that there was not a good enough connection between the soldered copper wire and the ends of the transistor and resistor. We solved this problem by burning off the copper enamel instead of scraping it off the ends of the wire. We tested the transistor by putting it into a circuit to see if the voltage changed. We tested the resistor by connecting it to a multimeter. We tested the LED by putting it in a series circuit with a battery and it lit up. We also tested the receiver coil to see if any current was being run through it by putting it in series with a multimeter in the current selection. Our next steps are to try this project with a different transistor and also try re-looping the wire to make sure all the wire loops were looped in the same direction. Another thing we could try is a joule thief circuit or light an LED by holding it above an induction burner.
After making our circuit and troubleshooting, our wireless power transmitter did not work. The LED did not light up and current never ran through the receiving coil. Even if we had the correct transistor, however, if we had the correct transistor, we are certain that it would have induced current successfully. However, we realized that the magnetic field could potentially induce current onto multiple loops at a time. This is the kind of idea Tesla was thinking of in his experiments. What's really cool about wireless power transmission is how practical it is in everyday life. What used to be a revolutionary physics concept is now incredibly mundane. For example, a wireless phone charging station uses this same concept to power your phone. However, in this example, the rectifier changes the alternating current back into DC, direct current, for the low-power device to be charged. The oscillator in this diagram is essentially the transistor that we used in our system. It produced an alternating current in the transmitter coil. And the short distance between your phone and the charging station makes this even more effective. Maybe one day Tesla's vision will be a reality, but still today we're able to admire amazing physics in our everyday life. It's even more enjoyable when you get to build something that uses these laws and concepts. From wireless phone chargers to electric toothbrushes, all use the power of induced current and magnetic fields. Hopefully, you too can see the uses of wireless power transmission in everyday objects around you and truly understand the physics behind them.